So I like to think of mechanism design as the engineering part of economic theory. A lot of the time in theory, what we do is we start with existing economic institutions, and we try to understand their function. And in particular, we try to predict the economic outcomes that these institutions give rise to. And this is the positive or predictive part of the subject. But in mechanism design, we do just the opposite. We begin by trying to say what it is we want by identifying the outcomes that we would like to have. And then we ask what kinds of institutions or mechanisms or games we could construct to achieve those goals. So it's very much a question of engineering, building something, a game, to achieve a desired outcome. And then, of course, we want to know not only whether such institutions exist, but if they do, what form they might take. So this is the normative or prescriptive part of the field, and it's the part of the field that has always most interested me. Well, so I've used a number of terms which I haven't defined, so let me spend a little bit of time talking about what I mean by some of these terms. First of all, what is an outcome? That, of course, is going to depend on the setting. And one possible setting is that of a government that's charged with providing public goods for the citizens of a country. So in that case, an outcome is simply going to be a choice of public goods such as infrastructure or national defense, environmental protection, public education, climate control, or whatever. But we can think of outcomes in different settings too. Let's imagine a political election. For the electorates in that election, an outcome is simply going to be the candidate who ends up filling the public office. In a more economic setting, we can imagine that there's someone with a collection of assets which he or she would like to sell off. So this person is an auctioneer, and there are a number of possible buyers who could get these assets. An outcome is simply going to be an allocation of the assets across the potential buyers. And finally, think of someone interested in having a home built for her family. And what she does is to engage a builder to construct the house for her. In that case, the outcome is simply what the house turns out to be. It's a specification of the house's various characteristics, together with whatever remuneration the builder receives for building it. So those are various examples in various settings of what outcomes might be. What might we mean by optimal outcomes or desirable outcomes? That's also going to depend on the context. In the case of the government and its choice of public goods, well, one criterion which is often used is that of net social surplus. That is, we look at the social benefits that these public goods create. We look at how much it costs to produce the public goods, and we subtract the costs from the benefits. That's the net social benefit, and that's the thing that we try to maximize. For an electorate, well, one criterion we might use in deciding whether the right person won is, would that person beat all other candidates in head-to-head competitions? That's not the only possible criterion, but it's a natural one. When we talk about auctioning assets, well, there are two criteria which are often looked at. Sometimes we're interested in finding the allocation in which the people who can make the best use of the assets, or who value them the most, end up getting them. That's the criterion of efficiency. Another possibility is that we look for the allocation which simply maximizes the seller's revenue or expected revenue. That's actually related to the first criterion, but it's not identical. There are important differences between the efficient allocation and the revenue maximizing allocation. And finally, for the home buyer and builder, we often use the criterion that whatever deal they strike should have the property that there is no other deal that they would both prefer. So this would be, say, Pareto optimality. So who is the mechanism designer? Who is the one who actually chooses the procedure by which the outcome is determined? That as well is going to depend on the context. In the public goods case, it's natural to think of the government itself as choosing the procedure by which public goods are determined. In the political case, normally the rules for national elections are determined constitutionally. That is, if you look at the American Constitution, there are rules by which presidents get elected, rules by which senators get elected. So we can think of the mechanism designers in the political case as being the writers, the framers of the political constitution. In the auction case, well, usually sellers get to call the shots, so we can think of the auctioneer as the mechanism designer in that case. And finally, in the house case, well, a mechanism in the case of the house building is the contract that the buyer and seller sign, because it's the contract which is going to dictate what actually happens, who owes what to whom. And so, since the contract is presumably negotiated between the home builder and the buyer, we can think of those two parties themselves as being the mechanism designers. Well, let's go back to the public good case. If from the very start the government knew which choice of public goods is optimal, say according to the criterion of maximizing net social welfare, then there would be an extremely simple mechanism for achieving the optimum. Namely, the government could issue an edict or pass a law saying this is what the public good choice is going to be. Similarly, in the auction setting, if the auctioneer wanted to achieve efficiency and the auctioneer knew which bidders placed the highest value on the assets, the auctioneer could simply go to those bidders and give them the assets, and that would be an efficient outcome. But the whole problem, the whole problem with achieving optimality, and what gives mechanism design some theoretical interest, is that presumably the government and auctioneer will not usually know enough to determine the outcome in advance. In the case of the government, the surplus maximizing choice of public goods depends on citizens' preferences, and there's no particular reason why the government should know these preferences in advance. Similarly, there's no reason why the auctioneer should know buyers' values for the assets being sold. So that's the difficulty for mechanism designers, and that's, as I said, why we're interested in studying the problem. If the designer knew the outcome in advance, the theory would be pretty dull. So mechanism designers have to proceed more indirectly. And the idea is to create a procedure or a mechanism which, in the course of its operation, generates the necessary information. So the leading questions in the field are, first, when can we actually design these mechanisms? And if they can be designed, what form do they take? And finally, we also are interested in the limitations. That is, we want to know when it's not possible to design mechanisms. And it might be helpful to go through an example, which is what I'll do in a minute. But first, let me point out that at this point it may seem at least mildly surprising that it's ever possible to design such mechanisms, because after all, it entails the mechanism designer attaining an optimal outcome when the designer himself doesn't even know what that outcome is, at least not at first. So that's why I think it'd be helpful to go through a little example. Very simple example. Let's imagine that there's a society that consists of just two people. We'll call them Alice and Bob, and this society is concerned with energy. So Alice and Bob are two consumers of energy. Energy is going to be provided publicly. There's an energy authority who has to choose the form that of energy that will be supplied to Alice and Bob, and there are four possibilities. It could be gas, it could be oil, it could be nuclear power, or it could be coal. And the authority has to choose one of these. Multiple choices are ruled out for technological reasons. Well, let's imagine that there are two possible states of the world that could obtain. In state one, these two consumers put relatively little weight on the future. To use economic language, they discount the future heavily. In state 2, it's just the opposite. They do put a lot of weight on the future. They have low discount rates. Now, let's talk a little bit about Alice first. Let's imagine Alice cares mostly about the convenience of the energy source. So in state 1, where she doesn't put much weight on the future, let's imagine that she favors gas over oil. So gas is her favorite choice, then oil, then coal, and then nuclear power. This is in descending order of how easy they are to use. In state 2, however, her ranking is different. Now nuclear power gets elevated to the top, followed by gas, coal, and then oil. And this reflects the fact that Alice anticipates that in the future there will be technical advances which make gas and coal easier to use, and in particular make nuclear a lot easier to use. So nuclear gets pushed all the way up to the top. Now, what about Bob? Let's suppose that Bob cares more about safety than convenience. So in state 1, where again the future is not weighted heavily, he puts nuclear at the top, then oil, then coal, then gas. But in state 2, nuclear goes down to the bottom. And the reason it does is because he's worried that in the long run there's going to be a difficulty with disposing of all of the nuclear waste that's going to be created. This is not a short-run problem, but it is a long-run problem. He also anticipates that gas will become safer because of technology. So what I've done here is to summarize Alice and Bob's rankings in the two states. And notice that they're quite different in the two states. Now, let's suppose that the Energy Authority is interested in choosing an energy source that is a good compromise between what the two consumers want. Alice and Bob have different views. The authority wants to reconcile those views. Notice that in state 1, oil makes a good compromise because Alice and Bob both rank oil second. Alice prefers gas, but Bob puts gas way down at the bottom. And Bob prefers nuclear, but Alice puts nuclear way down at the bottom. So it looks as though oil is a pretty good choice in state 1. We'll call that the social optimum in state 1. Similarly, gas, for analogous reasons, is going to be the social optimum in state 2. The problem is that the authority doesn't know the state and therefore doesn't know which of those two options, oil or gas, to choose. So what can it do? Well, one straightforward thing it could do would be simply to ask Alice and Bob what the state is. And if they both said it was state 1, then the authority might choose oil. If they both said state 2, then the authority would choose gas. If one said state 1, the other said state 2, they could flip a coin. That would be apparently a reasonable way of proceeding. The state is fixed, that's right. And so Alice and Bob know the state, the authority doesn't. The problem with this straightforward mechanism is that regardless of what the state actually is, Alice is always going to have the incentive to say that it's state 2. Because by saying it's state 2, she's going to raise the probability that gas gets selected. If Bob also says state 2, then gas does get selected. If Bob says state 1 and Alice says state 2, by having said state 2, Alice will at least have a 50% chance of getting gas. So it's a dominant strategy for Alice to say state 2, regardless of what the true state is. And we have the same problem for Bob. Bob has a dominant strategy to say state 1, regardless of what the true state is. So this simple mechanism, attractive though it may be, just won't work. It's too naive. So let's look at something slightly more sophisticated. What we'll do is we'll have the authority confront the two consumers with this 2-by-2 table. So Alice here is the row player, chooses the top row or the bottom row. Bob is the column player, chooses the left column or the right column. And I've indicated what the outcomes are as a function of Alice and Bob's choices. Now, let's see what will happen. First, let's imagine that state 1 holds. Well, the state 1 holds, and Alice expects Bob to play left. Alice will certainly prefer the top row because Alice prefers oil to nuclear power in state 1. Bob will prefer playing left if Alice plays top. And actually, the way I've set it out, Bob will prefer left. Oh, I'm sorry. Bob will prefer playing left regardless of what Alice does. So it's a dominant strategy for Bob to play left in state 1. So we get Alice playing top, Bob playing left as not only a Nash equilibrium, but it's the unique Nash equilibrium in state 1. And in fact, it leads to the right outcome, which oil is assumed to be the social optimum in state 1. So if we think of Nash equilibrium as a good predictor of what will happen, we will actually get the social optimum in state 1. Now, what about state 2? Well, in state 2, we expect that Alice will play the bottom strategy, anticipating that Bob will play the right strategy, because if Bob plays right, Alice has a choice between coal and gas, and she prefers gas, so she will play bottom. Similarly, Bob will play right if Bob anticipates that Alice is playing bottom, because Bob prefers gas to nuclear in state 2. So we have a Nash equilibrium where Alice plays bottom, Bob plays right, and this is the unique Nash equilibrium in this state. The outcome is gas, which is optimal in state 2. So we've done what we set out to, or the energy authority has done what it set out to. In either state, this mechanism produces the social optimum, even though the mechanism designer didn't know the states, and even though Alice and Bob don't care about social optimality per se. They're only interested in their own preferences. So we found a mechanism which reconciles the private preferences of the participants with the social preferences of the designer. And we say that this mechanism implements the designer's goals in this example. So what mechanism design theory attempts to do is to give some general answers to under what circumstances constructing mechanisms like this is possible, and when it's not possible. Well, if nuclear were at the bottom, then nuclear would have been. Are you saying that I should replace gas by nuclear?
Yes. What would happen then?
Let's see. Well, in that case, we would have a Nash equilibrium with nuclear as the outcome, and nuclear is not optimal, so that wouldn't implement. Oh, the designer doesn't know what the state is, but the designer knows, contingent on the state, what's optimal. That is, what the designer does is to think, what are the possible states that could occur, and what outcome is optimal for each of these states. I don't know as the designer which state actually obtains, but I know what the optimum would be if a particular state obtained. And so this is, you can think of this as this mechanism is not actually, strictly speaking, a game, because a game specifies payoffs as outcomes. And the designer doesn't know what the payoffs are, because the designer doesn't know what the preferences of the people playing the game are. This is what's called a game form, and the goal of mechanism design theory is to design game forms where whatever the state turns out to be produces the right outcome.
Yeah, but the designer knows the ranking of the preference ranking. Doesn't have cardinal utility information, but you assume that the designer knows the ranking.
Contingent on the state. It doesn't know. Well, in this case, there are only. This is a somewhat misleading example because there are only two states. But let's imagine that there are 50 million possible states.
You talked about what the social optimum is. You didn't talk about the relative preferences for different things. You just sort of.
I defined oil to be the social optimum in state 1, and I defined gas to be the. We could.
The ratings that he's talking about don't really come into this problem. The relative ratings, like Alice prefers gas to oil, but not by much.
Yeah. We could worry about those considerations too, but I'm not doing so in this example. Let me just say a brief word about where this theory comes from. There's a sense in which it goes back to the 19th century. There were various utopian movements, utopian communities in the 19th century, and the idea there was to escape the adverse outcomes of capitalism, which was burgeoning at the time. The more direct intellectual influence, I think it's fair to say, was a controversy that took place over 20 years or so, probably hit its height in the 1930s, It was called the planning controversy, and the idea there was that some economic thinkers, in particular Oscar Lange, Ada Lerner, expressed the view that if it were done right, they didn't say that it necessarily had been done right up till then, but if done right, they felt central planning could at least replicate a market system and potentially actually do better, because it was well known that there were certain market failures in pure market systems, and central planning had the potential for overcoming these. On the other side, von Hayek and von Mises argued vociferously that central planning was doomed. There was no way that it could replicate markets. The controversy generated a great deal of interest and a great deal of heat. There's a sense in which it was frustrating, at least for onlookers like Leo Hurwicz, because so much of the debate was framed in rather loose terms. There were notions like centralization, decentralization, being bandied about without ever being defined very precisely. And there weren't any theorems per se in this controversy. Everything was talked through, in part because the technical apparatus, which would have been appropriate for this debate, didn't even exist at the time. It would have been game theory, mathematical programming. So I think Leo Hurwicz deserves most of the credit for giving more precision to that debate. He was inspired to provide some definitions. He struggled over many years with an appropriate definition of decentralization. And he also showed how the technical tools could be used fruitfully so that we could actually get some conclusions, at least qualified conclusions, about what kind of system would work best when. Well, there was an enormous literature that derived from Hurwicz's work, and it more or less divides into two branches. There's work which takes place in very highly structured settings where we make lots of assumptions about preferences and lots of assumptions about technologies, and much of the work on public goods and auctions and contracts takes place in these settings where there are lots of assumptions. There's also been work done at a very general level, social choice, abstract level. My own work has tended to go back and forth between the two categories. But to conclude today's talk, I'd just like to tell you a little bit about some general results. So we have this notion of what it means for social goals to be implemented by a mechanism. And I gave you an example of where we actually implemented the energy authority's goals through a specific mechanism. But as I've already said, we want to be able to answer these questions more generally. That is to figure out how to sort social goals into the category of implementable or not implementable. And it turns out that there's a property called monotonicity, which is the key to implementation. So if social goals are not monotonic, then they're not implementable. If they are monotonic, then that's actually not quite enough for implementability.
Partial order wouldn't work. Instead of an order, you would have a partial order.
You're talking about for individual partial ordering for whom? For
Among social goals, rather than ordering.
So, all right. The definition of a social goal is, given the state, what are the optimal outcomes? So there's no ordering at all. We're just identifying what optimum or set of optima we want.
What was the definition of monotonic?
I haven't given it yet. Okay. I've mentioned the term, but now let me say what it is. So here, this is the definition. So social goals are monotonic if the following thing holds. Let's imagine that in a given state, state 1, outcome A is optimal. And now we move to another state, we'll call it state 2. And in this second state, outcome A does not fall in anybody's preference ranking. Then monotonicity says that given that A was optimal in state 1, A still has to be optimal in state 2. That's what monotonicity imposes. If A does happen to fall in someone's preference ordering and going from state 1 to state 2, then monotonicity imposes nothing. So to go back to the example from before, this was the example. And notice that in state 1, oil was deemed to be optimal. Now, oil is not optimal in state 2. Gas is optimal, but that's okay. That does not violate monotonicity because oil falls in going from state 1 to state 2 in Alice's ranking. It falls relative to nuclear and coal. So this is an example of a social goal which is monotonic. And we already saw that it was implementable. But now let's change the example a little bit. So here I haven't done anything to state 1, but I've changed the preferences in state 2 a little bit. And now nuclear becomes a plausible candidate for optimality in state 2. So let's say that nuclear is optimal. The problem is that these goals, oil in state 1, nuclear in state 2, are not monotonic. And the way to see that is to note that oil, which is optimal in state 2, doesn't fall in either consumer's preference ranking when we go from state 1 to state 2. Therefore, according to monotonicity, it should still be optimal in state 2, but it's not. Nuclear is optimal. And so there's no mechanism which will implement these social goals. And if there were more time, I would go through the reasoning, but let me just state the first main result. If social goals are implementable, then they must be monotonic in the sense that I've defined. Now, as I said, implementability is not guaranteed by monotonicity, but it's almost guaranteed. There's another fairly mild, or I'll argue that it's quite mild in many cases, condition that we can add on to guarantee implementability, and that's no veto power. No veto power just says that suppose that all individuals could agree that a particular alternative A is not only good but actually best in their rankings. And let's suppose that there's almost unanimous agreement. There's possibly just one person in society who disagrees that alternative A is best. Then, according to no veto power, this one person who dissents cannot prevent A from being deemed optimal. Now, one reason why I say that no veto power is weak is because let's imagine that an outcome consists, at least in part, of an allocation of goods across people. In that case, assuming that these really are goods, desirable, we cannot get nearly unanimous agreement that any outcome is top ranked, because each person will want all of these goods for himself or herself. That is, the hypothesis of no veto power cannot be satisfied. We cannot have two people agree that a given allocation is top ranked, because each wants all the private goods for his own selfish purposes. Theorem 2 says that as long as there are at least 3 people, if social goals are monotonic and satisfy this no veto power property, then they are implementable. Now you might ask, why do we need 3 or more people? And let me conclude with an explanation. 3 people actually isn't a requirement in all cases. In fact, we already saw an example, the energy example, where we could implement with 2. But having 3 people makes life a lot easier, and here's why. The whole problem in implementation is to try to get people who have different goals to do what the mechanism designer would like them to do. And in order to get these people to do what they're supposed to do, we have to give them a mechanism to play which aligns their own goals with those of the social planner. Well, in particular, what this mechanism has to do implicitly is to punish you for deviating from socially optimal behavior. But how do you know whether someone has deviated or not? In the case of two people, that's particularly difficult to determine, because if I've deviated and you have not, to the social planner, that may look very much like the situation where you've deviated and I have not. In other words, with just two people, there's a symmetry that pertains that makes identifying deviators particularly hard. Once there are three or more people, the deviators stick out more. If there are three people, two are behaving themselves, one is not. It's easier to identify the one who has failed to do what he's supposed to, and he can therefore be appropriately punished. Well, this is a very brief introduction to mechanism design. As you see, it makes very essential use of game theoretic ideas. And as I said at the beginning, my introduction to those ideas was from Howard and Duncan's book. So let me thank you.
We have time for a bit of discussion or questions or comments. Yes.
I had a question. Could you flip back a few slides to the chart of the yeah, right there.
This one, okay.
What would happen if in state two, both Alice and Bob preferred nuclear, but oil didn't drop?
Well, if Alice put nuclear first,
Right.
then oil would have dropped relative to nuclear for Alice, because originally oil is above nuclear, now nuclear is above oil. So
it's the relative drop.
yeah, no, the position doesn't matter. It's whether oil drops vis-a-vis the other alternatives. If it doesn't drop vis-a-vis any other alternative, then monotonicity says it must still be optimal.
Okay, that's what I was.
Yeah, right.
On the same picture, if you were using a border count to determine what's the optimal,
Yeah.
it's not clear that nuclear is better than oil, right?
Right. I'm not saying that there's any particular reason for concluding that nuclear is optimal in state two. You might think something else is optimal. I'm saying that if it's agreed that nuclear is optimal, if this is the social planner's goal or the mechanism designer's goal, then we're out of luck, because there's no way to implement these social goals. Deciding what method we should use to determine optimality is the subject of a different inquiry. That's welfare economics or social choice theory, and that's not what mechanism design is about. Charlie.
In your history, I think I probably would have added this literature on public choice that occurred in the 60s. And the interesting reason to add that is because the concept of implementability was more of a corporate game idea. The lecture yesterday notwithstanding. But in fact, there's a whole set of rich institutional design problems that involved out of there, many of which actually work and been experimental. So I probably would have added that to this discussion to show how really rich this idea of design and implementation is.
Good point.
Ken. Intellectual history. I think it should begin with David Hume.
Well, doesn't everything begin with David Hume?
There are passages of David Hume,
Yeah.
pure mechanism design.
Yeah.
And, the authors of the American Constitution must have read David.
Right. Hume has much to recommend him.
I feel a little guilty that Duncan and I weren't aware of this literature to include it in the games of decision.
Well, it had not really got. I mean, Hurwicz's work was just beginning to emerge at that point. So I mean, you might have heard about the planning controversy, but it was not. None of this had been made precise enough by the time you wrote the book for it to be included in.
You say something about at the beginning that you had trouble finding courses in the game theory.
Right.
And if we look at our common university, Harvard, there were a large number of courses that went under the name of bargaining and negotiation.
That's true.
And that, in fact, it was adopted so widely, and also widely in the law schools.
Yep.
And what happened at Harvard happened at Northwestern, etc. But there was a cultural difference between the economists and the people at the business schools and the law schools.
Right.
Here would be a very fertile ground of a commonality that would be of interest to both.
Well, there's still time.
I think we probably should move on.
Let's try another meeting.
Good. Here, here.